Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 chemistry students. Hi. Are you fine? I hope we are fine. I'm okay. And I'm Alan, who is still with you in the chemistry lessons. Welcome back. So today we are going in for Unit 15, having finished the other units. So this unit is called Radioactivity. Radioactivity. So of course, with radioactivity, it deals with radioactive materials and radiation. The word radiation, I'm pretty sure, is not new to you. You've always talked and heard of sun radiation. You've always talked of radiations from the radio, from the phone, and so on and so forth. So when we talk of radiation, that is not a new word to you. So we're going to be looking at the radioactive materials and how they radiate or how they produce radiation. That is all about radioactivity. You see a quick illustration on the slide. So, as we normally do, we need to have a quick unit competence roundup. At the end of this unit, at least these are the objectives that you should have achieved, or the competences you should have attained. You're supposed to be in position to explain the whole process of radioactivity in atoms, then develop awareness of the dangers of radioactive substances and the nuclear weapons. I think you've always heard of the war about the nuclear weapon usage, like in North Korea, in Iran, and so on. All those categories, I think you've always had them in news and so on. So we are to develop the awareness of what dangers do radioactive materials offer unto us. At the same time, we appreciate the importance of the radioactivity in our day-to-day lives. For instance, in the treatment of diseases, diagnosing them, and even in the production of electricity and other forms of energy. So that is what we're going to be looking at. Again, they can cause harm to us, but they are also important in our lives. So that is the whole unit competence aspect of it. And we can get started. I have a quick activity. I'm pretty sure, at least, if you are attending to this lesson, you're watching it on a television set, and being on the aspect that you're watching it, or you are watching it on your telephone or what, you're possibly seated comfortably in a room with a bulb or with some kind of illumination, a lamp or a bulb or what. So I want you to switch on that bulb or that lamp that you're using. Switch it on and see and observe. Switch it on and observe. If it is in the room, switch on your bulb and observe. What do you see? What did you see? Share it with your parent or with a friend that is close to you. What do you see after switching on that switch for a bulb? Highly likely, the bulb was lit, or you saw the light radiating in the room. The room became brighter. So if we can bring that understanding and say, this bulb emitted light, you see, and we use those sticks, as you see on the illustration, to imply the radiation of light. You see, we are using this to imply that light that is being produced, or the radiation, or the light moving within your room. Now, with this understanding of emitting something, let's compare it with the radiation and radioactivity. We've switched on the bulb in the room, and light was emitted. So the bulb has ability to emit light. And from that bulb, you can know the amount of light that has been produced or emitted, depending on the watts on the bulb. Is it a 5-watt bulb? Is it a 7-watt bulb? What is it? So basing on the watts of that bulb, you can quantify how much of the brightness you have in the room. Now, let's use this understanding or as analogy to radiation and radioactivity. Instead of the bulb, now let's substitute it with a radioactive substance. So, a radioactive substance emits, or it has the ability to release radiation. Different forms of radiation, but in most cases, the radiation, you can't directly see it. That's why I related it with the bulb. So there is a radiation being produced, and that is from a radioactive material. So this process of emitting radiation is what we basically call radioactivity. The unit of radioactivity is becquerel, and depending on amount of radiation you've been exposed to, that amount is measured in terms of sievert. So these are the terms. We shall come to use them later on when we're looking at the harm created by exposure to radiation. We are going to use these terms. So the emphasis in this case is about radiation. What does it imply? Can we bring it to real life? I can quickly compare it with the bulb emitting light. So a radioactive substance emits a radiation. So us understanding what exactly radioactivity and radiation are involved in, we can come to today's lesson content, which is about radioactive atoms and radiation. That is lesson 1 for unit 15. As usual, we need to know what we are going to focus on, the key terms, and the lesson objectives. So we're going to be looking at definition of radioactivity and the radioactive isotopes and atoms. Then we look at what are those particles that are emitted when radioactivity has occurred. Can we characterize them? And that is what we are going to be looking at. And we finally look at balancing nuclear equations. When radioactivity has taken place, can we balance and quantify what has been released? And that is the whole part of today's lesson. The key terms, we have radioactivity, radioactive atoms, and radioisotopes. Then we have disintegration or decay. We're going to be using that word, decay by those. When we say it has decayed, then we are looking at that part of disintegration. So objectives, you should be able to illustrate the properties of the emitted particles and rays. Those are alpha, beta, and gamma. Then balance correctly the nuclear reactions. I hope we are together. If you're a new student, do not worry, we are starting afresh, so you are not missing any part apart from the other units we've already finished. Now, let's go to radioactivity and radioactive isotopes. Again, I will pose a question unto you based on what we already looked at in our introductory part. What is radioactivity? What is radioactivity? What do you know about radioactivity? Basically, emission of radiation. But let's now connect it to the atoms. So radioactivity is basically the spontaneous disintegration, Spontaneous in a sense that it occurs by itself, though currently there is artificial radioactivity, but in most cases the natural radioactivity is the disintegration of heavier atoms into lighter atoms with emission of energy and some other particles. The aspect here is spontaneous and disintegration. It breaks down, disintegration. Spontaneous, it occurs by itself, naturally, it occurs. This is a quick illustration of radioactivity. So when you have a radioactive atom, it will disintegrate some part, releasing energy, radiation, and particles. As he said, radiation is actually not visible. You can hardly see it with our naked eyes, but it's always there. When we talk of energy, at least you've always heard of uranium and nuclear weapons. So that energy that is released when a nuclear weapon is blasted is what we classify in here as energy. And it is normally deadly, super deadly, that it creates abnormalities. We shall look at that in our consecutive slides. So, radioactivity, then radioactive atoms and radioactive isotopes. The heavier atoms that do disintegrate are the ones called radioactive atoms. Look at the slide and see examples. We have uranium, as I had already mentioned it, thorium, bismuth, all these are radioactive atoms. They disintegrate. Then, if you have, like uranium, some of its atoms also undergoing radioactivity, then they become radioactive isotopes. Radioisotopes are the radioactive isotopes of an element. Like you see uranium, this is one of them. This is a radioactive isotope. We have other more three. The unique feature here is they all have the same proton number, indicating they are of the same element, but they have different mass numbers due to different combinations of protons and neutrons. You understand the definition of isotopes. So that is the introductory part on radioactivity and radioactive isotopes. We are going to be using those words, radioactive isotope, or it is radioisotope, or it is radioactive atom. We've talked of uranium, thorium, and so on. There are actually very many radioactive atoms. Take a look at the periodic table. The ones I've given are the naturally occurring radioactive elements: thorium, uranium, and bismuth. But these are not alone. We also have the ones which are naturally existing, but they are very rare. So with the understanding of technology, man has decided to artificially make them. So they are called synthetically made radioactive atoms. Like these with a violet color. Then the purple are basically synthetic. Most of these are synthetic. But this is random, is a natural occurring, but very rare, so it is also synthetically made. Or actinium, and so on. So this is a periodic table showing the radioactive elements. You see there are very many, actually very many. As I said in our objectives, we are to look at the characteristics of the emitted particles. When disintegration has occurred, can we characterize the components that have been given out? Yes, it is possible. And how? By subjecting them to electric field. And how they behave within that electric field, then they can be characterized. So you see, if you're having a radioactive a sample of an atom, and it disintegrates, and you let the particles pass through electric field, the components of the disintegration behave differently. If it is alpha, it is always attracted to the negative side of the electric field because it has positive charges. It is a helium particle or a helium atom, so it has positive protons which will be attracted to the negative side of the electric field. Beta, which is an electron, is always attracted to the positive side of the electric field because the positive attracts the negative here. And the gamma ray, it is not charged at all, so for it, it is not affected within the electric field. It goes straight. Now, with this experimentation, which was earlier done by Rutherford, you remember the atomic structure, the particles are generally classified and characterized as you see the table. Let's quickly go through it. The nature, what is alpha? What does it imply? It is basically a helium nucleus with the mass number 4 and proton number 2. Having proton number 2, that indicates it is charged. It has a positive 2 charge. That's why it is attracted to the negative plate in the electric field. Then, and by mass number, you see it. And that is what we've looked at. Then the beta, it's an electron. Electron, they don't have weight. Their mass is 0, but they have a charge. They are negatively charged. And as such, they are deflected to the positive plate in the electric field. Then the gammas, we said this is just electromagnetic radiation. It will not be affected by the electric field. It has no charge and no mass. Now, last point, I did not mention it. We can look through it. The penetrating power. And this is where the aspect of nuclear disintegration becomes harmful to our body. The penetrative power of these particles and rays released. Gamma rays, which we can't see by using our naked eyes, they have high penetrative power. So they will actually pass through our bodies. And this illustrates their penetrating power. You will have your paper. The simple paper will shield you from alpha, which is a helium. But it won't shield you from the beta particle, which is an electron. And it will hardly do any harm on the gamma rays or the X-rays. They will simply pass through you. And of course, with that, they will cause other body effects like cancer and so on. So in the presence of aluminum shield, at least the beta will be obstructed, but not the gamma rays. The gamma rays are normally shielded by the lead. The lead shield is what protects people working in the nuclear weapon industries and so on. They're normally shielded by the lead to prevent them from exposure to these X-ray and gamma rays. Since we can't see them, they are just electromagnetic. And as such, we look at the decomposition or the decay depending on what is released. So if the atom disintegrates by emission of alpha particle, that is the helium, there are some changes that occur. Remember disintegration, or remember the definition of radioactivity, it's about spontaneous disintegration of bigger and heavier atoms to form lighter for more stability. So this is what happens. If you have, for instance, radium, disintegrating by emission of alpha particle. Remember we said disintegration is same as decay. Now it will yield a lighter atom. This is random now. From 82 number of protons and 226 mass number to 222 mass number and 86 proton number, with helium being produced in here. So what do you notice? The atomic mass decreases by 4, atomic number decreases by 2. If you have any alpha emission, using this example that we are having, the daughter atom will have atomic number which is 2 less compared to the parent atom, and it will have the mass number which is 4 units less compared to the parent, as you see. And as such, normally alpha decay leads to the daughter atom to be 2 places to the left in the periodic table. I need to pause around here, and you first understand this before we can move. To help you come up with this value, this is the equation right here. Look at radium and radon. Let's look at the periodic table and see how they relate. Let's see how they relate. This is radium, and this is radon. You see, radium to radon, we move 2 steps. One is francium to here. Left. I will take you a little bit back to maximize that point. With alpha decay, the daughter atom is 2 places to the left. 2 places to the left of what decayed, and you get this. Let's quickly look at the beta emission. Beta emission, since it emits an electron, we only expect the change on the proton. The proton will stay inside the nucleus,